Hello, this is Richard Hammack's Calculus 1 course. We are in part 3 of the course on derivatives. Today, lecture 28, Logarithmic Differentiation. Logarithmic differentiation is a technique for finding derivatives that combines properties of logarithms with implicit differentiation. It's not something that you'll use every day, but occasionally it's useful. You might have a function that you need to differentiate, and none of the rules apply. Sometimes logarithmic differentiation can find a derivative. And other times you might have a very complicated function that the rules do apply to, but in applying them it's going to be really messy. In a situation like that, logarithmic differentiation can organize your work in a way that gives you an answer quickly and neatly. So our goal here is to use logarithms to help compute derivatives. So the first thing we're going to do is review some relevant properties of logarithms. Now in calculus, when we say logarithm, we're almost always talking about log base e, or ln. So that's how I'll phrase this review. Remember that ln of ab equals ln of a plus ln of b. Taking the ln of a product converts it to a sum in the manner described here. Ln of a over b equals ln of a minus ln of b. Ln of 1 over b is minus ln of b. And ln of a to the power of b equals b ln of a. Of course, there are other properties of logarithms, but these are the ones that we're going to need today. You've had lots of experience using these rules, so you should be pretty familiar with them. I want to point out one pitfall. When we say, for instance, ln of ab equals ln of a plus ln of b, what we mean is that that equation holds provided that both sides are defined. And you can find situations where one side is defined and the other side is not. For example, imagine a and b both being equal to minus 1. This side is ln of minus 1 times minus 1, which is ln of 1, and that's 0. What about the other side? It's supposed to be 0. Well, it's ln of minus 1 plus ln of minus 1. And ln of minus 1 is not defined. So this rule kind of breaks down in that case. So when we state this rule, we're tacitly assuming that both sides are defined. As long as both sides are defined, they're going to be equal. Now we can patch up that problem of a or b being negative by putting everything in absolute values. You can check that ln of the absolute value of ab always equals ln of the absolute value of a plus ln of the absolute value of b, at least provided neither a nor b is 0, because ln of 0 is not defined. And this is the way we're going to use our rule today, for the most part. Ln of the absolute value of ab equals ln of a, absolute value of a, plus ln of the absolute value of b. In the same way, ln of the absolute value of a over b equals ln of the absolute value of a minus ln absolute value of b. And ln absolute value of 1 over b is negative ln absolute value of b. And additionally, ln of the absolute value of a to the b equals b times ln of the absolute value of a. And this holds whenever a to the power of b is defined. So these are the relevant logarithm properties that we'll need today. We also know how to differentiate logarithms, and I want to remind you of those formulas, the review of logarithm derivative rules. Remember that the derivative of ln of the absolute value of x equals 1 over x. And sometimes when we don't care about x being negative, we're only thinking of x as positive, we might not take that absolute value. the derivative of ln of x equals 1 over x. And here x has to be positive, so it's in the domain of ln. These two are essentially the same rule. This one's a little bit more general, so that's the one we use most often. Applying the chain rule to this rule gives the derivative of ln of the absolute value of a function g of x equals 1 over g of x times g prime of x, or just g prime of x over g of x. And if g of x is always going to be positive, or if maybe we don't care about the x's that make it negative, we'll sometimes write this as the derivative of ln of g of x equals g prime of x over g of x without the absolute values. But for the most part today, we're going to stick with the absolute values. And finally, if g of x is y, if you have y equals g of x, this rule might be written as ddx of ln of the absolute value of y, which is the absolute value of g of x. That's the derivative of y divided by y. So ddx of ln of the absolute value of y equals y prime over y. Really, that's just a rephrasing of the rule that's above. But this form is going to pop up numerous times today, so I just want to call it to your attention. And of course, if this function y is always positive, or if you don't care about it being negative, if that's not a part of the problem, then you just write this as the derivative of ln of y equals y prime over y. But again, for the most part, we're going to use this rule that has the derivative ln of the absolute value of y equals y prime over y. So these are the relevant properties and rules that we'll use today. And we're also going to rely heavily today on the process of implicit differentiation. So let's get started. We'll begin with a motivational example. And well, really, this is going to be several examples. We'll start off simple as a warm-up. If y is equal to x cubed, you can certainly find the derivative of that. Y prime is 3x squared by the power rule. Switching the roles of x and 3, if y were equal to 3 to the power of x, that's an exponential function, and we have a rule for that too. Y prime is 3 to the power of x ln of 3. So here comes the twist on this problem that will illustrate in logarithmic differentiation. Imagine you had y equals x to the power of x, and you want to find the derivative. What would the derivative be? Well, notice that this is not a power function, because a power function is a variable to a constant power. So we can't use the power rule. Nor is this an exponential function, because an exponential function is a constant to a variable power. So we can't use the rule for the derivative of a to the power of x. So we're in a situation here, it's very interesting, no rule applies. There's no rule that matches x to the power of x. So how are we going to find the derivative of that? Well, here's our strategy. And this is really what logarithmic differentiation is all about. Our strategy is this. Before differentiating, take ln of both sides and simplify. So let's follow that strategy. We have y equals x to the power of x. That's what we want to find the derivative of. And take ln of both sides, or more precisely, take ln of the absolute value of both sides. You get ln of y equals ln of x to the power of x. Why would we do this? Well, remember on the previous slide, we had a property involving ln of a to the power of b, or ln of the absolute value of a to the power of b. It was b times ln of the absolute value of a. So applying that rule over here on the right, we get ln of y equals x times ln of the absolute value of x. And look at what happened in that step. We took ln of both sides, and we simplified using an ln property, and suddenly the exponent went away. This side on the right is x times ln of the absolute value of x, and we can find the derivative of that. So our next step is going to be to take the derivatives of both sides with respect to x. Now on the left, we have d dx of ln of y. This is the derivative with respect to x of y. So it's not d dx of ln of x, it's d dx of ln of y. And remember, y is a function of x. In fact, it's the function we're trying to find the derivative of. So right here on this side, we're doing implicit differentiation, the derivative of ln of a function of x. And we know from the previous slide that that derivative is y prime over y. It's the derivative of the function y divided by y. That's just our rule for the derivative of ln of g of x, g prime of x over g of x. So that's the left-hand side. What do we get on the right? Well, we're differentiating a product, so we've got to use the product rule. So that's the derivative of x times ln absolute value of x plus x times the derivative of ln of the absolute value of x, which we know is 1 over x by our derivative rule, familiar now and also reviewed on the previous slide. So notice that we're looking for y prime, and we said no rule applied. We're at a point right here where y prime appears in an equation. And we can solve for y prime. In fact, it's really easy. We could just multiply both sides of this equation by the denominator y. So first of all, let's simplify here. 1 times ln of x is just ln of x, and x times 1 over x, that's 1. So we have y prime over y equals ln of x plus 1. And now let's multiply both sides by y. So we get y prime equals y times the quantity ln of x plus 1. And we've now isolated y prime. But notice we have both x's and y's over here. We need to get all x's. What do? Well, remember that the y is x to the power of x. So we can replace this y with x to the power of x. And we've got our derivative. Y prime equals x to the power of x times the quantity ln of the absolute value of x plus 1. That's our answer. Y prime is x to the x times ln of the absolute value of x plus 1. So that's pretty good. Given that no rule applied, we were able to find a derivative. And what was our strategy here? Take the function y equals f of x, take ln of the absolute value of both sides, simplify using ln properties, differentiate implicitly, and then solve for the derivative. That got an answer when no rules applied. And that process is what we call logarithmic differentiation. To differentiate a complicated function f of x, like this f of x equals x to the power of x, first of all, write the problem as y equals f of x, as we did here. Secondly, take ln of both sides, or more precisely, ln of the absolute value of both sides. Then thirdly, simplify using log properties or ln properties, as we did here. Then step 4, differentiate implicitly. And finally, what's the last thing we did? We solved for y prime. That 5-step process is called logarithmic differentiation. Let's look at another example involving this process. How about the derivative of x to the 5th sine of x all over x plus 1 times e to the x? Imagine you needed to differentiate that function. In looking at it, it's a quotient. So you would start off with the quotient rule, and that would involve the derivative of the top and also the derivative of the bottom. But look at the top, it's a product, so you'd have to be using the product rule inside the quotient rule. And the denominator, that's also a product, so you'd be using the product rule twice in applying the quotient rule. And you can see that although that's doable, it's not the most fun problem in the world. I want to show you how logarithmic differentiation can quickly give you an answer. Let's carry out this 5-step process. First of all, to differentiate this function f of x, write it as y equals f of x. So here we go, y equals all of this. Take ln of both sides, and by that I mean ln of the absolute value of both sides. So that's our next step. And then third, simplify. Well, you can't do much with the left-hand side, but the right simplifies a lot. First of all, that's ln of the numerator minus ln of the denominator, all in absolute values. And then the ln of the absolute value of x to the 5th plus sine of x, we could break that up too using logarithm properties. That's ln of x to the 5th, ln of the absolute value of x to the 5th, plus ln of the absolute value of sine of x. And on this side, breaking that product up, that's ln of the absolute value of minus 1 plus ln of the absolute value of e to the x with the negative distributed in there. So we're breaking this function up into simpler pieces, but we can keep going. Ln of the absolute value of x to the 5th would be 5 times ln of the absolute value of x. And over here on the other side, ln of the absolute value of e to the x, well, e to the x is positive, so that's just ln of e to the power of x, and we know that's just equal to x. So now we've completed step 3. I don't see any way we could simplify this further. So we'll move on to step 4. We differentiate both sides implicitly with respect to x. Now on the left, the derivative of ln of the function y is the derivative of y divided by y. That's just our old familiar derivative rule for ln of g of x. On the right, well, we've got the derivative of the sum of some pretty simple functions. The derivative of 5 times ln of the absolute value of x is 5 times 1 over x, right there. Then we have the derivative of ln of sine of x. That's the derivative of ln of the absolute value of g of x. So that's going to be g prime of x over g of x. In this case, it's cosine of x over sine of x. Then minus the derivative of ln of the absolute value of 1 plus x. That's the derivative of 1 plus x divided by 1 plus x. So that's 1 over x plus 1. And also don't forget to bring down that minus. And finally, we get the derivative of minus x. Well, that's minus 1. So we're almost done. We're looking for the derivative, y prime. We just multiply both sides by y. And we get this. But now we've got apples and oranges, we've got x's and y's, it's supposed to be all of x's. Well, just remember that the y that's right here, it started out life as this function. That's what it's equal to. That's what we were differentiating. So that's what goes there for the y. And there's our answer. We could clean this up a little bit, maybe the cosine x over sine of x, write that as a cotangent x, maybe. But here is our answer. This is our derivative. And maybe this seems like a lot of work, but you might want to compare by working this out using the quotient rule combined with the product rule. It might be a little more involved. But there are two routes you can take here. That's one of them. The other is to use a logarithmic differentiation, as we've outlined in this example. Next, we're going to revisit some derivative rules. Imagine that you need to find the derivative of f of x times g of x. Well, that's something that you already know. That's the product rule. The product rule says the derivative is f prime times g plus f times g prime. But I want to show you how you could actually use logarithmic differentiation to come up with this answer. You would write y equals f of x times g of x. So you're looking for the derivative of that. You'd take ln of both sides, or ln of the absolute value of both sides. You'd simplify, differentiate both sides implicitly with respect to x, and you get on the left y prime over y. On the right, the derivative of ln of f of x is f prime of x over f of x, and the derivative of ln of the absolute value of g of x is g prime of x over g of x. We then multiply both sides by y to isolate the y prime. And remember that y is f of x times g of x. So putting that in, we get this. And now multiply the f of x times g of x into the parentheses, distributed in there. When these two terms multiply, the first one, the f of x cancels, and that gives you an f prime of x times g of x. And when you multiply times the second, the last term, the g of x cancels, and it gives you f of x times g prime of x. So sure enough, you get the expected answer, f prime g of x plus f g prime of x, as expected. Now this is just a quick little illustration of using logarithmic differentiation to find an answer that we already knew. But I next want to use it to find an answer that we don't already know. In this next example, or application, we're going to prove that the derivative of x to the power of r equals r times x to the power of r minus 1 for any real number r. And that's just the power rule. The derivative of x to the power of r is r times x to the power of r minus 1. But don't we already know that? If you think about it, we don't already know that. Way back in the beginning of part 3 of the course, when we deduced the power rule, we only deduced it for values of r that were positive integers, like 1, 2, 3, 4, and so on. And then when we got to the quotient rule, we showed that it worked for negative integer values of r, like r equals minus 1, or minus 2, or minus 3, and so on. And at that point, we said, it turns out that the power rule works for any value of r, and we're going to use it that way. And we did. The derivative of the square root of x for us was the derivative of x to the power of 1/2, which was 1/2 x to the power of 1/2 minus 1, and so on. We used the power rule freely, even though we'd only proved it for integer values of r. So now we have to come back here and actually prove that we were justified in using the power rule the way we did for arbitrary values of r. We're going to prove the power rule using logarithmic differentiation. So imagine you wanted to show that the derivative of x to the power of r equals r times x to the power of r minus 1. You want to find this derivative. The first step in logarithmic differentiation is to write that as y equals x to the power of r. The next step, take ln of the absolute value of both sides, then simplify using ln properties, and there's only one thing that happens here, the r comes down. And once you've done that, you differentiate implicitly with respect to x. At this point on the right, this constant of r by the constant multiple rule can come out of the derivative. So let's bring it out. And now let's take those derivatives. The derivative of ln of the absolute value of y is, as we know, y prime over y. On the other side, we get r times the derivative of ln of absolute value of x, and that's just r times 1 over x. We're looking for y prime, so we clear out that denominator, multiply both sides by y. We get y prime equals r times y over x. Now think about what y is. Y equals x to the power of r. So let's write that y as x to the power of r, and let's write the x on the bottom as x to the power of 1. And now with exponent rules, the x to the power of r divided by the x to the power of 1 is x to the power of r minus 1. So here is our answer. The derivative of x to the power of r is r times x to the power of r minus 1, just as expected. So this shows that the power rule really does work for any real value of r. And we can freely and with license use it that way. The derivative of x to the power of r equals r times x to the power of r minus 1. Does that make you feel better? It should. So as a quick example, let's take the derivative of x to the power of pi. That's a pretty strange function, but it has an easy derivative. We can use the power rule. The answer is pi times x to the power of pi minus 1. So in summary, we have this interesting and sometimes useful technique of logarithmic differentiation to differentiate a complex function f of x, write it as y equals f of x, take ln of both sides, simplify using log properties, differentiate implicitly, and finally solve for the derivative. So get some practice. I think you'll find this technique useful at times. Next time, coming up, we're going to talk about a topic called related rates. And after that, we will be done with part 3 of the course. We'll move on to part 4. So I hope to see you then, and goodbye.